Okay. Okay, I think that's everyone. Sweet. Awesome. So, yeah, I just want to say thank you for everyone for coming. We have a few fallen comrades, particularly Angel, rest in peace. So, yeah, so a few things, which is the source code for this talk is on this repo. You know, if you want, you can run through it yourself. It's kind of easy to run it. You just clone the repo, go spt run, it will run all the code. The best way I think to do it is like go through, like uncomment some kind of print lines to see how that works, manipulate the data. And yeah, so let's get straight to it. I'm going to...
Are you recording this?
Yes, I am recording this. How does Zoom work again? You share, project. Cool. Okay, so the last thing we worked on last time is we looked at particularly the reader monad. And remember, the reader monad was talking about how specifically functors, specifically functions, we can define both a functor instance. Sorry, this is just getting into the loop of things. We can define both the functor instance and a flat map instance for those. Now, for those in the room, what does that mean? The methods that are now defined on functors. If it is both a functor instance and it is a monad instance, it has what? What can we call on those functions?
Map and flat map.
Yeah, cool.
Pure.
Yeah, flat map, pure, or flat. You know, those are the four things we can kind of call on that function. So there was one thing that Angel mentioned at the end, which was, personally, I think what I did was I made a mistake by showing you all the implementation of how the reader monad worked. And what Angel said was something along the lines of, we have this monad abstraction, we don't really care how it works, but we know that when we do this, we've defined, by chaining each of these operations together, we now have a function that takes some sort of value, threads it into each and every one of these parameters, and it allows us to yield results from all of those functions, being fed in chain. So that was what, this is what that code does, and we can understand the kind of result that it spits out. And we don't really care about how the implementation works, because that is something that is third party, is controlled by the monad abstraction. Everyone following so far? Sweet. So what I'm now going to do is, we saw sync, right? Here's sync. We liked sync because what it did is it allowed us to suspend some sort of effect. And in functional programming, what we like to do is we like to move all our, side effects out from this code here and out to some sort of edge of the program. So here, when we create this value, it doesn't print the line, it doesn't get the line. But when we call unsafe interpret, there's the side effect. The side effect is at the edge of the program, right? Because we are functional programmers, that's what we want to do. There should be some sort of way to have some sort of almost variable, some sort of stateful thing that we can put data in, pull data out. But when we do that, we are pushing that side effect to the edge of the program. That is a reasonable thing for us to want, in much the same way that we can suspend these kind of side effects, these I/O side effects. We want to suspend this idea of writing and reading from some sort of reference. I'm going to show you this, and I'm not going to show you the implementation. So here we have this thing, we have this computation that it's of a type state, and it's parameterized by the state of that data type. So the data type is, the state is integer, some int, and it can also return some auxiliary value. In this case, it's string. When I run this, what pops out? I want someone to just guess. Just zoom in a bit, sorry.
The final value is 8.
Yes, The final value is A. One of the final values is A. The thing that it returns is the final value, and the final value is 8. So it's returning this result of the computation, which is a string, and it's returning the final state as well, which is an int. And it behaves like a function, because what we do is we cram in some initial value to this thing. Are we all okay with just accepting that this is a thing that is a monad, because its interface is map and flat map? And there's the FA, or there's the F, and there's the A for our flat maps. If we can we accept that this is a monad that has that interface? Do we need to see the implementation? Or can we just accept that this is something that we understand intuitively how it works? Or those who want to see the implementation, or those who are okay with ignoring the implementation? Ignoring? Cool, awesome, because the implementation is a bit spooky. The really cool bit is, now we're just going to start using that monad interface, and that's how we reason about how its behavior works. And we're putting all the scary stuff about how this actually works behind that monad interface.
What is the initial value?
So if I put in 1, that would become 9.
Oh, I see. It's a
Yeah.
function. Okay.
Yeah. Oh, actually, it would be the same value, right? Because we're putting
That's
10,
basically more.
right?
Yeah. I like, what does that first modify? Like, I was confused. What was it operating on?
The state itself.
Yeah.
Right.
So.
Cool. So, if I did this, what would it spit out? What would this come out as?
8 and the final value is 9,
Yes. Why?
because we never put it back in.
Correct. We didn't modify the state. We modified what this would result with. So we did the get, and we mapped over the result of the get. And then we bound the result of the get to last. Speak now if that doesn't make sense, because we can look at why. Cool. Awesome. So, now that we have it's just asserted that this exists, we're going to use this later on. Cool. So before in last talk, we looked at how functions compose. And here's a function that takes a family member and gives their mother that may or may not exist. Does this work? Probably not, given this sad face. Why doesn't it work? Just looking at it. Remembering that map is function composition. How can you compose a function that returns an option of family member with itself? They don't line up, right? This would work if it was a family member to a family member, but it's a family member to an option of a family member. You'll see the type checker catches up, that'll eventually error out, right? Because it's going to say, I expected, yeah, here we are, it's saying, what the fuck? I required an option of a family member, but I found a function that went to a family member. That started, the domain was of a family. So it's kind of like, oh shit, that's not good. That's code we want to write though. You know, that kind of sucks. And here's another one, right? We have a function that knows how to get our mother, right? And then we want to compose that with a function that gets, well, that should be mother. Right? Compose that with a function that gets their age. We should be able to write this function, but we can't, because it's saying this mother, yeah, it's an option of family. Oh, shit, right? It's kind of annoying. We shouldn't, we want to write, we don't want this function to have to understand how options work, to deal with the fact that the age may or may not exist. You know, we just want it to get the age, right? So we're kind of in a tricky situation because we've already written code that understands how functors work. So my computer's just gone black. There we go.
Zoom seems to have crashed here.
Demigods have cursed me.
Is the power supply plugged in and switched on? Sometimes it's like hibernated.
Yeah. Oh.
Some dodgy CCTV, like guy stabs
The guy stuff somewhere with Scala in the background.
Jeffrey Epstein has turned the camera supply off. Yeah, cool. We've already written. If this was an option and we would do this map, this would work, right? But we have this function that returns an option, and this map no longer works. It's now getting this option here. The types aren't lining up. So what's happened is our maps no longer work in the way that we want it to. And we're going to have to use some other thing that changes how these maps work. That's what we want. We want to build code that does this for us. I'm just going to comment this out. So type checks. So,
You might
Yeah, the screen is
restart
frozen.
if you want.
Shit.
I mean, will it disconnect, reconnect, I guess, from the screen maybe? Or actually, maybe it's just totally frozen.
it's completely fucked. Ah! Yikes, dude.
Can you end the meeting of that? That recording's gonna be so fucked.
Well,
Oh, I ain't gonna pass
that still works.
Can you kick yourself for the meeting?
Okay.
There's two maxes.
Yay.
Alright, we have
That's
a
the
new
most
max.
terrifying thing
Oh my god.
That's better.
If you share your screen, you should kick a old max. Don't do it.
Don't it? Yeah.
Fuck the recording. Can you share screen from your?
Yeah, but then now there's two of me.
No, but that's not.
That's
not a
that's
problem.
okay.
That's not a problem.
I'm going to leave the meeting, keep the meeting open, rejoin.
But
That's not gonna
that's
work.
not going to work because that's making the smart screen leave the meeting, not your laptop.
So wait, what do
The fact that there's the old you in the meeting isn't a big deal. As long as your new one shares your screen, you'll kick the old one off the share screen.
Yeah.
That's right.
Oh, old one's gone anyway.
Okay. Cool, we're back. All right, cool. We're in business. So I was just saying we need something to change how map works. And we have a scary name called Kleisli. And what Kleisli does is you wrap it around a function that returns some sort of monad and it changes the behavior of how our maps and how flat maps work. We're going to get to that in a second. But intuitively, can someone explain what this is doing? Just by staring at the types. Imagine if so we have some Kleisli, and it takes a function that takes some A and returns a monad B. If I crammed my getMother function here, whoop, right into there, what does this map now do? And what does that map? So now this is a Kleisli of something, right? getMother, right? Because we've crammed it into the Kleisli. So now this is going to be a Kleisli now. What are the type parameters of that Kleisli?
Int?
Option.
Option. Yeah.
Option.
And then
Family member int.
Yeah.
option family member int, I think.
Option, family member. Correct. That is correct. That will now work. That will now type check. Because what it's doing is the map here is it's running a map on the monad. Or where's the monad? Can't see from this angle. There's the monad there. Which is that there, right? It's actually, funnily enough, that run gets this out here, sorry, and then it composes the function that we really want to run. Holy shit! Now I'm fucking confused. No. Actually, what it does, right? So it gets out this, right? There's the run. It maps the function.
Yeah, it's just
So
composition.
It does a map to get you that, and it does another map to get you that.
Mm.
It's going through two layers. Remember when we had our R to our A of something, and when we did our map, it took our A to B. It allowed us to get the A.
Yeah.
With the Kleisli, it allows us to get the FB and then the B, which is nice. It's going through two layers. It's going through the function and then the monad at the end. Tell me if I've freaked anyone else out. All good?
So it's the function composition with the maps in between, right?
A little bit. Yeah. So it's doing going through two ways. It's doing two maps. Cool. So, Kleisli. You can map over Kleislis, and it's changing the behavior of some underlying function. Now this works. And it also has this fun little, we also define this auxiliary function called that there. Before we wanted to do function composition, and we saw that this did not work. Here what we wanted to do is we wanted to compose one function with this function. And here we wanted to use this to modify a family member into an age. And they both had the same name. Kind of works for functions, but it doesn't really work for Kleislis. Because, that was a bad explanation. But we also have on Kleislis, we have this function called andThen. What andThen does is it takes one Kleisli and another Kleisli, puts them together. So now, this works. So now we have some sort of get mother, we wrap it up in a Kleisli, and we can chain our Kleislis together. And then we do a map at the end to convert the family member to get their age. And then we call run to unwrap it. So that's the code we wanted to write in the beginning. And Kleisli has allowed us to do that. Pretty dope. Awesome. That's a reasonable thing that we might want to write code for. That's what Kleisli is doing for us. As you can see, we can call great mother age on me, gets that age. It's pretty awesome. We like that. Everyone good so far? Cool. So we're seeing this idea that Kleisli is modifying some sort of function that returns a monad and changing its behavior. It is also a monad. It's a functor because it has map. Also has a flat map. Okay. I'm going to show you this code. And this is like a little kind of, we define a bunch of auxiliary functions. So this is a function that takes some sort of HTTP request, and if its method is post, it's like, sweet. Cool. Otherwise, it's like, no, didn't like that. Here's a function that has a body, it just gets the body out. Here's a function that takes a map of parameters on that request. As you can see, map string to string. And it tries to get that header out. Here's a thing that it will try and pass a JWT token, and if it succeeds, it just puts the token in the claims. Kind of weird, bit contrived. And here we have a function that it's just called extract JWT, and it tries to extract a header, and then it tries to pass it. That's code that we might want to write at some point. That makes sense. You know, nice little compositional pieces of code that we're trying to go together. And then here we have another function. It takes a request, and if that request was made by an administrator, it says either yes, I could confirm that, or no. Absolutely no idea. I couldn't either pass the JWT, or they didn't have an authorization header or something. Cool. This does not type check. Can anyone explain to me why it's not type check? Okie dokie. Here's a function extract header, it's turning an option of string. And here's a function that takes a string to an option of a JWT token. And it's shitting the bed because it's saying, you've given me a function that takes a string and gives me an option of a JWT token, but I am trying to compose that with a function that returns an option of string. It's not working. We can fix that with the class. Now it works. That'll type check in a second. Cool. Because now that's how, and then composition works. It takes two functions and glues them together because it knows one as both return monads. We know how to glue monads together. It's with FIDO. Cool. That's what Quais was doing for us. Type checks. Why doesn't this type check? That's returning an option of a JWT token. And here is a function that takes a this is a function that takes a JWT token, right? JWT token. And it's upset because when we map it, it returns, we're composing a function that returns an option of JWT token. But here's a function that takes just a raw JWT token. That's upsetting. We know how to fix that. You can do it with Quasar. Now it works. Cool. Now this is the really interesting bit. Remember how we saw back up here? Oh, I've gone past it. Sorry, there's a lot of fucking code here. Yeah. We take some sort of parameter and we return a bunch of stuff, and then each of these functions is taking some value that we've thrown to them. If we go back here, we can kind of see that that's exactly what we're trying to do. This function takes a HTTP request. This function takes takes a HTTP request. This is a function that takes a HTTP request. What's trying to happen is we want to feed the same HTTP request to all of these functions. And at exactly the same time, all of these functions can fail with the option at the same time. It can either exist or not exist. What is the type? What right now does Scala probably think this type is here? Given that extract body takes a HTTP request, returns an option of string. What would this be?
It wants an option string. Oh, sorry.
Sorry, this is technically wrong at the moment. Right. This does not type check. So that is going to be an option of string. because that's how monads work for functions. You know, it passes that HTTP request to that function, that function, and binds their results to that. Yeah? Cool. How do you think we fix this?
Wisely.
Wisely. We fix it with wisely, right?
So what's the problem we're trying to solve, sorry?
The types don't line up.
Okay.
So what will happen is it's trying to, it's binding this. We want this to be a string, right? We can't get the body. This computation doesn't make sense. We can't check whether it's a post request. Like if it doesn't fail, whether it's a post request or not. Just we'll return some option.
So the problem is like the value after binding the value we get after like the
Is an
flat
option.
map is an option, and we
Yeah.
want it to be there.
And we want it to be just the thing inside the option as well. We want to thread the function, we want to thread the value through the functions, and we want to get into the option as well. I want to do two things at once, right? Remember the two things at once that I was saying before? Is this map function that we were saying? Does two things at once. Does a map and does a map. Okay, it goes, composes the function and maps over the option, or the monad, whatever it is. So we have this, you know, we want to do two things at once. So what we do quasars, right? And that type checks now. We're taking these functions and wrapping them in quasars. So obviously, if it's working in for notation, this Kleisli is a monad. Do we want to read the implementation? Or can we just accept the fact that what this does is it is a monad, so we can use it in for notation. And the behavior of Kleisli is it is both doing the reader, it's pushing that request into each of these functions, and it's chaining the options that they resolve with. Which means that this is the behavior when we run this function. It's a post, and it's an admin. Right? It's an admin and has a body. This successfully responds. If it doesn't have the correct authorization, it shits the bed. And if it's a GET request, it shits the bed. Fails out, doesn't work. And that is reasonable code that we would like to write. You know, and we've used this Kleisli thing that we've built for this specific purpose to get that to work. Any questions so far? Cool. Kleisli has another name called reader T. They are the same thing. They're used in different contexts. And it's called reader T because it transforms a monad and adds the reader behavior to it, where that behavior is threading that value to all the functions that return monads. Cool. Any questions? Let's keep going. Remember our little sync monad that we had before. So little sync monad allowed us to suspend some side effectful kind of behavior. Oh shit, is this recording still?
It's got a rec symbol in the top left.
Oh, sorry. Okay. We can suspend some of these side effectful functions. There's put string line, right? Suspending this print line. We have this get string line which suspends some reading from the standard. You know, that's cool. You know, that's a monad. If I were to run this, what would it do? This like friendly echo function. If I were to copy paste this into the command line right now, what would it do? Or into the REPL. Anyone?
It wouldn't run it.
It wouldn't do jack shit. Because what is happening is it's already a sync, right? Right? And it won't evaluate that. And it is also, if we desugar this wisely, it's a string to a sync of unit. And what it will do is when we run it, we first have to provide it the string that it will now thread to each of these functions. And then what it will do is it will chain all these functions together in the flat map we saw from our first lecture, or second lecture, sorry. And then we have to run it, unsafe interpreter, and all run. So we've used this wisely, this reader T, to add this reading behavior to sync. It's modified both the option monad and added this reading behavior, and it's added, we've also used it to add this reading behavior to the sync monad. And we push all the side effects, to here. It's like reading from some context, we're pushing that value into all those functions. And it is also, this is deferring that computation until we call unsafe interpreter. Cool. Any questions? Brilliant. If this is all that you took from this talk and you understood this section, good. That was like, kind of useful to understand. It will probably help with Atlassian account and, contributing to it. We use Kleisleys for zip tracing. A lot of our, modules, they don't return a HTTP response. They return a Kleisley to something else of the HTTP response. So that tracing works, that everywhere we can actually access the original HTTP request and, see details about it so we can do like nice tracing and modules. We'll talk about that later. Next section. Now this is a section that I'm more comfortable with people not understanding. But if you do get it, awesome. There's a bunch of data types that have this notion of almost a binary operation between them. For example, if I have, say, a number and a number, two integers, can someone name a binary operation that operates between these two things?
So what was the original
A binary operation.
addition?
Yeah, addition, right? 1 plus 1, 1 plus 1, there's the binary operation.
Finally, something I understand.
Yeah. Lists. What's the binary operation between two lists?
Concat.
And concat, which is the plus plus operator in Scala. Well, what's another example?
Strings.
Yeah, strings, also lists of characters. So there's a bunch of data types that we can encode this idea of like there is a thing that operates between two of them, it's just binary, right? We also have this notion of the identity, where when we do the binary operation to one data type, that doesn't change. So what's the identity for integers under addition?
0?
Yeah, 0. What's the identity for lists?
Empty list.
Empty list. Sweet, cool. And so some things have that identity, like we can, some types have that sense of an identity, some don't. And so what we do is we define two type class instances, one called semigroup, one called remote. So semigroup encodes this idea that there are types that have this binary operation between them. So if you have some A that is a semigroup, and you have another one of those A's that is a semigroup, there you can run this operation between them, and you get an A, which is a semigroup. And then monoid is this idea that you have this identity. So let's look at some instances. Lists, the operation is appending. For ints, in this instance, we have operation is addition. And for maps of arbitrary keys and values, we have what is a right biased union. If they share the same key, we take the value on the right. And that's some nice, beautiful imperative code. Love it. Mwah. You know? That's some nice stuff. And here we are for, monoid, define the identities. We have empty, we have 0, and we have an empty, empty map. Yeah, sweet, that works. And here's a few demos. Ta-da! That should return 1, that returns 1, that returns 3, right? So we have this operator that works on any monoid, whatever the fuck we want it to be. Cool. Now we have this idea of like fusing things together naturally makes sense that like you have a bunch of monoids in a list. We can get all those things in that list and smush together into one value, right? This just makes sense. It kind of adds up everything in the list and concat. And here's another one that kind of does something very similar.
Is there a special property on the object that's passed into mconcat that allows it to do that?
That the things inside the list are themselves monoids.
Okay, but the container of the list is can it be a list, a sequence, or
We've specialized this to the list.
okay?
So does anyone want to hazard a guess what this implementation looks like? And concat. What's it doing? Yeah, it's going to do a reduce. What's it reducing with?
The monoid operation.
Yeah, and what else as a collector?
Well, the additional accumulator would be whatever m empty is.
Yeah, the entity. Yeah, sweet. Yeah. Reduce, fold, what the hell? With the identity element and that operation between it. Having everything in this list and swoosh. And this is like generic across any monoid. We've seen how type classes are nice before. If we have evidence that this is M is a monoid, it will work. Cool. So that's this is a bit abstract at the moment. Unfortunately, I couldn't find monoids don't really crop up in an Atlassian account, so I couldn't find any examples to be like, oh, this is kind of something that's kind of useful. So this next bit's going to be a bit brain melting. There is this function that you will find in a bunch of functional programming standard libraries called mconcat_map. And you look at it and you're like, why would you give that a name? It's like flat map. It's a map and a flatten. Why have you made it a specialized function? And we find that flat map is like very useful and allows monads. So that's kind of cool. It's a useful function. mconcat_map is one of those functions because it finds itself in a bunch of weird situations where it is the idea of giving map and then an mconcat a name kind of conveys intent. Much the same way flat mapping conveys the intent of chaining things, computations. Mconcat map is that kind of conveys that intent. Now, I'm not gonna kind of want to see everyone's answers to this. What do you think people use this function for?
Transforming an array of something initially and then collapsing it down.
Yeah, collapsing it down, right? That's like what it does literally.
Could it be used for like some kind of parallelization?
Yeah, maybe. Right?
I know where this is going.
Yeah.
That's kind of useful. Why would we want to change the interpretation? Maybe. The implementation's the same. This does stuff, this doesn't do stuff. And this is like the real result. Maybe that's a test result that we want to like test certain things about. Kind of useful.
Mocking or whatever.
Yeah, mocking. That's why it's got a name, because people write programs and do interpretation and they get a result. And the property is that this M is a monoid. There's this idea that we have a program which is this sequence of some G, some sort of grammar, and that we're interpreting it and then combining it down to some final result. Cool. I want to write a file system. I'm going to write a program that does a bunch of operations to that file system. We want to define an interpreter that takes each operation in that program, interprets it into some subresult, and combines all those subresults into a final program. I want that behavior to change based on whether we're in production engines. Cool. Let's do that. First of all, we define what our program is consisting of. And our program consists of a bunch of little case classes, little data constructors. Contains a bunch of information, write file, read file, delete file. And then what we do is we wrap them up in lists. Because we want to smush these things together to form a big program, which is our list of operations. Here we write our program, we write a file, we delete a file, and we write a file. Here we have our function, our interpretation function. Takes each of those operations, commits a side effect. Writes some stuff. There we go. Here we have a read file, prints some lines that it's read, and here we have a delete file. And then we return our monoid. We're going to get to that. Here we have our test interpreter, where rather than using a real file system, we use a map, which kind of simulates our file system. When we write a file, we put an entry in that map. When we read a file, we don't do anything to our file system. It doesn't do anything. And when we delete a file, we don't really have a way to actually modify the map, so we write none. Because it's write biased, we'll delete the old value. Wipe it with a none. Let's run this code. Scala compiler. Is it? It's in the. Not in this window. Okay. Cool. Share. Oh Jesus Christ! That's not what I wanted to share at all. You're fortunate because it still hasn't compiled. There we are. Come on. Holy shit. There we are. Cool. There's the result of our final, of our file system. Holy shit. There we are. Sorry, there's the result. As you can see. Boop. A text, some vain text, some B. Yeah, that's nice. Look at our file system. We have, oh shit. Let's run that again, to be honest.
Can you hide that bottom bar on the screen?
Yeah, I'm starting to think that this was a mistake.
There's actually a hide button for it.
Checking the 3 dots.
It's on the screen. Max,
Yeah, I know.
Right, it looks like nice. It's like weird on Scala.
How do you open the fucking terminal?
You're working on that.
Holy shit. Oh, you know what?
So weird, you're going.
Oh my god. The demo gods.
Trying to Google that lock and buttons. Weekend. Jesus Christ. Sorry, I might be joking.
Oh no. Oh no. Jesus. Yeah, look, fuck it. It works. Yeah, it does. Oh, Jesus. Oh, you've got the fucking lock. Yeah, anyway, oh god, it's resolving dependencies. So we have this function. Sorry?
Should we just come back in an hour?
No, we'll be fine. Anyway, this doesn't. Okay, so that worked. Trust me, it wrote files, and we got a result out of this thing. Does this function work? Yes or no? We write this code, will it do what we think it will? We have a write, we have a delete, we have a... Sorry?
What was the signature of delete file again?
I missed it.
What's the type signature of delete file? Okay.
Delete file does... Oh, it's a list of files. Right? Delete file returns a list of file operations.
They'll return this.
So will this work? No. This read file returns a list of file operations. We get that list of file operations, chuck it the fuck away, and then we delete a file, and then we write a file with what is a list and with what is a string. One, that does not type check. And two, this operation here is never getting integrated into this, which is our list of file operations. Yeah? So this doesn't really work.
Nice.
Does it delete button work?
Just accept it.
Hell yeah, dude. Okay. Kind of annoying. Shit. Do I like end the talk? I don't know what to do.
It's fine.
It's fine.
Okay, cool. Alright, so this function doesn't work at its core. It's not going to work because this read file isn't integrated into this file, right? Let's look at what this list is. It's a list. In this case, this is not actually how the lists that we've been using so far are actually implemented. But lists are this kind of almost recursive definition where they're a link of a value to the rest of the linked list. And here we're building that list. It's a link to a 1. A link is like a 1 to the rest of the linked list. Of a 2 with the rest of the linked list to an n. So we're creating this data structure and we're embedding values into it. And then when we do a map, for example, we dig our way through that structure to run functions on the things embedded in that structure. Cool. See, that would work. Love it. You know, awesome. That's what a linked list is. And then there's another issue with this prod interpreter. Because what it is doing is, remember what I said I wanted to do with this function. I wanted a program and then I wanted to interpret this G to some subpart of the final program. And then we'd smush all those subprograms down into a program result. There's nothing really wrong with our test interpreter. We got by with that, you know? We took our fake file system, we smushed all our fake file systems together, and, you know, it worked. We changed the values and we could delete the old values. But this kind of was a bit of an issue because we committed these side effects, but we couldn't really return them because they committed side effects. We returned this list of unit, which was us effectively giving up and returning something that didn't really represent each subpart of the program. What was happening is we weren't really pushing the side effects to the edge of the program, which was what we did before with sync. We did successfully push our side effects to the end of the program. We pushed our side effects into the interpreter, but we didn't return what was in here. We returned this. So this prod interpreter is wrong. It's not correct. We want to return something else that embeds those side effects. And also this is kind of ugly. We kind of just want to map string to string. We want to delete our old values without having to overwrite them with a new value. My question is, what do we return from here that would be nicer? I've shown it to you actually before. There's something we can return from this function other than a list of strings. Or a list of units, sorry. So?
Lightning?
Sync. Sync was an embedding of side effects that we could return from this. We interpret some sort of subprogram into some part of the grammar, some list of instructions into a subprogram. And then we get all those subprograms and smush them into something else. What could we return from this that would do what we want, in that the fact that we want to delete something actually properly from this map? What's some sort of subprogram that we can chain together? Yeah. So we want to change, we want to return this. Here we want to return a sync. And here we want to return a state. Why can't we return those? I want you to look at this type signature again. Why can't we return state and sync? They're not monoids. They're monads. Right? So we want some function where this is the monad. Well, I'm not going to write anything anymore. I'm kind of scared. Actually, does this still work?
I wonder if the undo button does it. Hey.
Yeah, it's awesome. You know, we want some sort of monad here. And we want to interpret it into some sort of monad of type A. This is some sort of monad, maybe like this. Monad, you know, something like that. That kind of could be pretty cool. So list is an embedding of just, you know, your raw values. You know, we build this data structure, we embed these A's into this kind of structure. And then we kind of can traverse through this structure with this like map function. Kind of recursively goes through that structure that has all those A's in it. And we can interpret them, right? This is where the free monad. Now, if you don't get this, don't worry. It's hard. But I'm going to try and do it. I'll show you something. Oh, shit. Actually, no, that's not where. So, we saw that mconcat map before, right? Took our monoids, took our list of the instructions, and it took our interpretation from those list of instructions to the subprograms and smushed all the subprograms together. There is this function called foldmap, where it takes not monoids, where it doesn't deal with monoids, it deals with monads. And it takes some structure, some recursively defined structure, some sequence of instructions called free. And it takes some function that interprets those instructions to monads, that's the monad, and returns some smooshed version of all those monads. Are we okay with that function existing? There's a few little questions about this that are like, what the fuck? Are we okay with thinking that this is a useful function to make? You know, pretty cool. You know, there's data structure called free,
There's a squiggly arrow.
and the squiggly arrow. So what a squiggly arrow is this. Squiggly arrow, G to F, is the same as GA to GF. Oh, sorry, FA. GA to FA. That's what the squiggly arrow does. Takes some thing of some type and returns it to some other thing of that type. So a valid thing would be option to list. And I could give, when I would apply to this, if I were to give it a sum of 5, I would reasonably expect a list of 5 or something like that. That's a valid natural transformation. That's what that squiggly arrow is called, right? There's a function from options to lists and should preserve the type that is inside both of those types. Everyone following so far? Reasonably? Before I show you the actual implementation, which is going to be really fucking terrifying, I'm going to show you what we actually write. And it looks exactly, well, I'm saying exactly, but it looks very similar to the code we wrote before. We have a bunch of data structures tagged with their return type. Ooh, kind of cool. When we write a file, we expect nothing to happen, right? You know. When we read a file, we expect a string out of it. Hell yeah. We're reading a file. When we delete a file, we expect some no kind of return type. We can make it a boolean if it's succeeded or failed, but we're actually not going to do that without implementation. Rather than, actually I'm gonna v-split this to show you the similarities. Rather than wrapping them up in lists, we wrap them up in frees. As you can see, suspend. Different kind of function, but it takes these data types and wraps them up in frees. As you can see, I'm just going to move this over. You can see it's returning frees instead of lists. Free, 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 free. Here we write our program. Looks very similar. We have a write file. Here we're using a little concat function. Sorry, a little binary operation. Here we're doing exactly the same thing, but instead we're using patterns. So the operation here that we fused our little subprograms together was this concat function. And here we're using patterns, which is kind of like a little concat function. And here's another program. Kind of useful. Because now it uses our append function. That will work. Because that append, before, if we go back up, you'll see that, there's append, this read file returned a list of file operations. But now, our friendly little, oh Jesus, where's our append file M? We'll see that our append, that is now, come on. Anyway, it's a string. You know, that's a string, right? And obviously, because we're doing this in for notation, free is a monad, right? Here, lists were a monoid, and we could fuse them together with this operation, and we were embedding values into that thing, which is the list. We were embedding those values into the monoid, and then we were interpreting those values to a monoid, and then we were collapsing those values down to a monoid. Here, we are embedding just arbitrary things like this into a monad, and then we have an interpretation function that takes those things into a monad, and then we are smushing the final value down into a monad. And then here's our interpreters. We take our operations, we return syncs. As you can see here, we're taking our side effectful functions and suspending them. We're returning a sync now. We're taking our side effectful function, we're suspending it, we're putting it in a sink. Side effectful function, putting it in a sink. And here's our interpreter. It's returning state now. So we're getting our modify function. We're modifying our map, our test state. We're taking our operations and turning them into states. Returning a state, returning a state, right? That works now. If I can get it to fucking run, hopefully. There we are. Here's our, first of all, we're going to do our test interpreter. Ooh, shit. YouTube run. So, look at the program. Here's our program. Program M, write file. What will the map be? Final map. If you look at that, we have AM text, we write AM, we delete AM, we have BM, we write BM, and then we append CM.
bm.txt bmcm.
Yeah, there we are. There we go. BM txt BMCM. And what we've got is we have our program, we run our fold map with the interpreter. No, sorry, over here, yeah. We have our fold map, we have an interpreter that returns a state, and then we run with our empty value against that state. That's our initial value of that state computation. It works. Sweet. Now, shit, sorry. There's a lot of fucking scrolling going on here. Perfect. So here we are, we have our program. We're going to use fold map with our prod interpreter. And if we run it, nothing happens. But now we have a sink, we run it at the end. We've pushed our side effects to the edge of the program. And when we run it, it should do the thing. Come on. Take your time. Take your time. Cool. Look at our file system. Okay, BM. There we are, BMCM. Worked. Awesome. That was a lot. I think I did an okay job of explaining it. Any questions?
So is this like the only use case for the free monad, or is there anything else?
Pretty much. It's an unfortunate use case. It's definitely a use case. All the use cases, it is one of them. So yeah, we take some grammar, we embed it in the free, we sequence our program together with our flat maps. We have different interpreters that take those operations to monads. We can run our monads. We can create our final monad. We can run our monad. We have a test interpreter. We can run our monad. We can invoke our monad. We can run out the effect of our monad. Cool.
Just to answer that question, we use it for all our clients to talk to other services, for example.
Yeah.
That's the majority where we use Atlassian account.
And in Atlassian account, we interpret those things to state. That's how we use state. We have you usually have a map for some sort of value that we're pushing data to. And we do interpret our stuff to sync, or the Atlassian account equivalent of sync. Cool. Does anyone want to know the implementation?
Yeah.
Oh, actually, before we do that, why is it called the free monad? It's called free because the list is called the free monoid. It's called the free monoid because what you can do is you can take things that are not monoids, which are G's, you can put them in the list for free. It's very easy to just wrap things in a list. And then later on, you can turn them into monads. In the free monad, you can take things that are G's that are not monads, You put them in the free monad, it's just called free, and you later turn them into monads, right? This is the process of later turning something into a monad, where the things that we're embedding aren't monads. So we're going to see why that works. And here is quite possibly the most really terrifying Scala that you'll ever see. This is like looking into the heart of the darkness, you know? Tune out now if you've understood so far, because your mind's, yeah. We create this trait called a natural transformation, right? It's a function. You know, it takes some f, it takes some higher kind of f and returns a higher kind of g, right? There's the f of a and it has to return the g of a, right? And then we give it a little alias, which is the squiggly boy. Yeah, squiggly arrow, right? And so what we say is a free is, remember how we looked at our linked list before? Linked list, it's a link and an end. That is the data structure. It's links and ends. And it contains A's. Frees are three different types of things. They're pures, suspends, or flat maps. Where instead of embedding just the A's, we can embed A's or G's of A's, or frees of G's of A's, and other functions of A's to frees of G's of B's. If we look at this data type, flat mapped, can you see how you have a free of G of A to an A of free of G of B? What does this function look like? Looks like the flat map method on monads. So f of A to an A to an f of B returns an f of B. And flat mapped is data. That was a function. This is a data type that contains a free of G of A to an A to a free of G of B and returns a free of G of B. So when you're flat mapping on your frees, you're not doing anything. You are just adding more flat maps to the free. Not doing anything. When we had lists and we were doing the n concats, remember how with our numbers, when we go 1, n concat, so that binary operation 2, took the 1 and the 2 and we fused it together to a 3, right? What happened, we took one value and another value and we fused them together to give a completely new value. All the old stuff's gone. Fused, bam. With lists, when we take one list and another list, we fuse them, right? It doesn't destroy the old operations, it gives an entirely new value where the old parts are together. That's the free monoid. The free monad is taking, when you have a free and you flat map another free, it doesn't do something. It doesn't destroy the old parts in the process of the flat map. It's fusing them. Oh, it's not fusing them. Yeah, it is fusing them. It's not destroying them. It adds it adds a flat map. Much the same way a list doesn't destroy the old parts, it just adds a new link. This adds a flat map. This is a bit advanced for people. Sorry, David. This is to the Peters and the Jameses in the room, and maybe the Joes and the Justins. So,
How would you do like conditional stuff with monads?
With monads?
Or
With
like
free
how
monads?
would you do it in like that kind of for comprehension stuff?
You'd run if.
Just an if?
Just run if statement. Make sure both ends of the branch return a free.
Okay.
It will work.
So just like some like no op free.
Yeah, pretty much. That no op free is pure. In much the same way monad for is pure, free is pure.
My next question would be, what is suspend then? Because
Suspend.
pure and flat mapped makes sense.
The suspend is fun. So pure takes some A and puts it in the pure, right? And suspend takes some G of A some A that is already in a G context,
Yeah.
and also puts it into the free.
So it doesn't lift it, it just,
It's a different type of lift. You need a lift for raw A values, and you need a lift for already contextualized values in the G. And we're going to get to why that is. So this makes sense. Pures. Flat maps. They are both, rarefied operations on monads, where the operations themselves, the pure returns a pure, the flat map returns a flat map. It is the operation returns a data type, or produces a data type. And the suspend returns a suspend. Yuck. Map, what it does is it's a flat map of a pure, right? Because that makes sense when you take, free of G of A and you have an A to a B that's free of G of B. Flat map, this has to be a free here, so we just pure the value, and it works. Remember that was the thing that we showed back here in our first talk. We were kind of looking at our, over here, we're kind of like, oh yeah, we can go flat map pure, and that'll still work. Remember that first talk, our second talk we did? That's what that definition is.
Can you just go back to it for a sec?
Oh, sorry,
No,
what's
no,
that?
the free one.
The free one? Yeah, I'm just going back to the free one now. Ah! Yeah. Flat map pure. Because the flat map is going to flatten that layer out, right? And to get that to type check, if we had that, it would check bed because it's going to be like, I expected a free here. So we have to pure it up. Now, this is the cool bit, the real fun bit. Here's the implementation. Here's the implementation of fault map. So this is interpreting those G's of A's into the F's of A's. Pures contain raw A's. So to get it into an F of A, we do a pure of F on that A. Suspend contains a raw G of A. We have a function that describes how to get a G of A into an F of A. So we run that natural transformation on that G of A to give our F of A. Makes sense. Doing our interpretation. Flat mapped. Oh boy. We have an F, we have a free of A. And here we have an F that is an F, is an A. F is an A to a free of F of B, right? How do we get, if I were to just,
a free of FB or a free of G?
let's rewrite this. First of all, we have our F of A. How do we get our F of A into a G of A?
Wait, are we getting F and G the wrong way around?
Oh, sorry.
Yeah.
That's actually, yeah. Sorry, that's F gar. Sorry.
In that type signature that you've written on the right,
The right.
Yeah.
is that free of G of B?
Because
Because when we created the
yeah. Sorry, free of G of B. That's Sorry about that.
Should we call it like G rather than F? Oh, I guess it's still a function.
It's technically F.
That works, whatever.
fact.
Maybe not.
Hold on!
Okay.
Okay. Anyway. Okay, how do we get, so we want to get to some f of a at the end, right? And we want to integrate the result of what this f is into that final monoid. Given that this is your free of g of a, how do we get it in to an f of a? This fold map takes a free of g of a and returns the f of a, right? What we need to do is we need to recursively call that, right? We are a free, we're in a free context. We need to run this fold map again on that sub computation to get it into our target monad. Cool, that works. Now that is now a monoid. Oh, sorry, a monad.
And
Of FA.
presumably the recursion eventually reaches a pure or a suspend, so we're not.
Yeah. That's cool. We like that. So now, there's our f of a. How do we get the f of the a into this f?
Pure function?
No.
No, what?
So it's an f of a. We have a function that takes an a to a free of g of b. And this is an f, where f is a monad. Flat map. Cool, right? Flat map, right? So there's our, oh shit. So at this point in time, come on dude. Oh, it's freaking out on me. There's our a. Now we have our f of a. What does that return? What does that f of a return? A free of g of b, right?
Yeah.
So we fold it again. So what we do is we run the sub computation, which returns a monad of a. We get the a out, we return it to the next link in the chain, which gives a monad, and then we integrate them back with the format. That was a bit brain melting. But the cool bit is the type system does not let you do anything else. So it's like, Scala's pretty cool. That works. Thanks for the presentation. I'm pretty.
The second fold map is
Zero.
getting me a bit.
The second format, yes.
Yeah.
So there's the f returning the free, right?
Yeah.
But the free, this here returned the monad, the final monad that we wanted. And then this flat map takes that a, runs that f. Now it's
So whatever the result of that function is, we need to do interpretation on
we
that.
do need to do another layer over here. And then we run that second interpretation. And we fuse them together, right? With that flat map.
Yeah.
Bam.
We haven't done anything with FGA though.
Out of this FA, it's just changing it.
Oh, yeah, whoops.
Yeah.
Done. There's free for you. Pretty cool, right? That's the end of the talk. Sorry. But you can kind of see how arcane free is. But at the same time, quite elegant.
So
So,
it's basically, like conceptually, it's sort of building up the, so to take a really shitty analogy, for if you've got like a program,
Yeah.
you have an AST and then you have like a semantic tree, whatever the hell they call them.
Yeah.
That's basically what free is for monads, right? It just has a structure that you can represent
Yeah.
with monadic
Represents
computations.
some monad, but we don't know what yet. And
Yeah.
eventually do the real interpretation to make it a real thing.
Yeah.
That makes sense.
dope. Awesome. Any other questions? Otherwise, I think we're done.
I have questions, but I don't think I can absorb any more answers.
Yeah.
Thank you.
No problem.
Very good.
Thank you.
That's answered something I've wondered about for a long time.
Thank you.
Big wave to the recording.
Bye.
You're not in frame, Max.
Potatoes.